Okay, hello everyone. Welcome to the third plenary session, the 3A session of FRB 2021. This session is focused on repeaters. My name is Emily Petroff. I am currently jointly hold a Venny Fellowship at the University of Amsterdam, and I am a project manager in the CHIME FRB collaboration in Canada. And it's my very great pleasure to host this session, and we will get started very soon. A few notes about the session itself. So I haven't been to any of the session 2 yet. I'm waiting for the 2B later this afternoon, my time. So it's very fitting for me that the first one that I went to is populations, and then we jump straight into our most interesting population of all, the repeaters. So it makes perfect sense to me. But I'm very excited to hear from the speakers that we have in this session, most of whom will be presenting live. A few housekeeping notes for people attending. If you would like to ask a question of the speaker, please use the Q&A, not the chat. And I will try to read your questions out at the end of each presentation. We ask that if you do want to ask a question in the Q&A, you need to have your name attached to your Zoom account. We won't be reading out questions from anonymous accounts, so please do just register with your name so that we can get to your question. And if your question is not answered or you want to elaborate on the discussion that's happening, you can join the FRB 2021 Plenary 03 session on Slack and have more discussion there. Okay, so with that, I will wrap up and I will hand it over to our first speaker of the session, Mohammed Chamma, who will be talking to us about the spectro-temporal law between sources of repeating fast radio bursts. So Mohammed, you want to share your screen?
Sure. Thanks, Emily. Hello, everyone. Is my screen showing okay? And my
Yes,
audio
it's great.
working? All right, thanks. So hi, my name is Mohammed. I'm a PhD student at Western University. I'm just starting my last year. Today, I'm going to be talking about evidence of a shared spectro-temporal law between sources of repeating fast radio bursts. This is work that we first submitted last December. And then there were some concerns from the referee about the robustness of the result, given how the DM is chosen. So we redid our analysis and we rewrote a lot of it. And that's what I'll be talking about today. Just to get started, I'm going to talk about the triggered dynamical model. So this is kind of a model we came up with to describe how we imagine the FRB process. There was an earlier talk by my colleague Fareshte Rajabi in the previous session. There's a lot more details there in that talk, and I will just be giving like a quick summary. So basically what we imagine for FRBs is we have a trigger and the source is in front of that trigger along the line of sight to the observer. We don't know what the source is. What we do assume is that it has some velocity, and the source could be moving away from us or towards us. And most importantly, we assume that the FRB emission is happening at a single frequency, nu naught. So it's a narrowband process from the start. That's our assumption. And we also have a timeline for that process. So what we imagine happening is that there's a trigger that happens behind the source. And then there's some kind of delay time. And then after that delay time, the FRB emission begins, and that lasts for a certain time, tau W. So the model doesn't assume any physics about what tau D are, what tau D or tau W is. We just assume those times exist, but there's lots of room for extra physics to go into this model. These are basically all the assumptions that go into it. So what we do then is, assuming the source is moving relativistically, is we kind of transform this timeline into our own reference frame. So from the FRB reference frame into our reference frame. So that's just a Lorentz transform, and then you take into account a relativistic Doppler shift, and we can derive this relationship between the subburst slope and drift rate. I'll talk about slope in a second. And it's in terms of the frequency that we observe it at, the FRB at. This term here is the slope and sometimes the drift rate. And then we have this constant out front, which is in terms of the times. And it's inversely related to the duration in our reference frame of the FRB. Okay, so let's talk about what I mean when I say slope versus drift rate. So this is some terminology confusion that we had early on, but so I just want to make sure this is clear. So I have here some data from Gajar. It shows multiple bursts within a single FRB, multiple subbursts. And when people talk about drift rate or sad trombone, we're talking about essentially drawing a line between the center frequency of each of these subbursts and measuring the slope of that line, roughly speaking, or essentially that's what's happening. And really what we were trying to study was the slope more particularly. And the slope, what we mean by that is just basically the same thing. So frequency over time, but within the individual subbursts. So for our model is mostly predicting things about the slope. There are predictions about the drift rate, but we really want to focus on the slope to start. But we will see that these two measurements, while at first they seem distinct, can be closely related. So how do we obtain these measurements? So we're using the autocorrelation technique that was described in Hessel's 2019. Where basically you take your fast radio burst, your waterfall, you compute the 2D autocorrelation of it, which will almost always give you a nice elliptical Gaussian-like shape that you can fit a 2D Gaussian to. And from the fit parameters of that fit, you can get things like the subburst duration. You can also get the angle that the Gaussian is rotated. You can use that to calculate the slope, the subburst slope, as well as the drift rate if there were multiple subbursts within this waterfall. So this is a good technique because it's repeatable, it's easy to automate, also handles fast radio bursts with complex structures. You can have strange shapes, but you'll always get something that is more elliptical and more Gaussian once you compute the autocorrelation. So when we want to measure these parameters, the question you hit immediately is what DM should I use when I'm measuring when I'm measuring these things? And the reason that's important is because if you have a waterfall and you'll just vary the DM you've chosen even slightly, you'll rotate the autocorrelation function, which will change the value you get. So for example, for the slope, of course, over here, I'm going to get a very large number for the slope. It's very steep, and here I'll get a much larger number. So, that's a big problem. You can get like a huge range of measurements based on your DM choice. I have here an example also from Gajar 2018, where they talk about two choices of DM. So here you have a fast radio burst, and it has several bursts within it. And if you choose a DM that's found by optimizing the signal to noise ratio, what the algorithm is going to do is it's going to stack the components of the fast radio burst to increase the signal to noise, and you'll get a DM that's high. So in this case, you get a DM that's 600. But if you had a different algorithm, like if you chose a structure parameter and chose to optimize that, which would preserve the structure of the FRB, and you choose the DM that way, you're going to get a DM that's much lower. So in this case, you get 565. So this is a choice this is a problem you have to deal with when you're trying to decide which DM to choose before you perform your measurement. One thing you could do, so we're trying to look at as many bursts as possible. So one simple way is to just take the published DM for each burst and use that and hope things work out. But there's a problem because a lot of these bursts are not available at very high time resolutions. So it's hard to tell if they're resolved. So here, for example, it looks like there's maybe 2 bursts here. And then as soon as you don't know if your FRB is resolved, it's really hard to decide between a structure optimized DM and a signal to noise DM. So my answer to the problem of what DM should you use when measuring an FRB is, why not all of them? So what we do is we just pick as many DMs as possible. We pick a range of DMs, and we're trying to be as conservative as possible. So we want every plausible DM, and we're going to repeat our measurements at each DM. And this is going to give us a range of measurements across the DM range. So This is going to give you very large ranges. So it's going to be a large range of measurements, but it turns out to be accurate enough to determine if the relationship the prediction that we've made with our model describes the data. So that DM range is going to be chosen based on the history of the source, how it changes with time. You can look at the sample of the bursts that you're using, see the distribution of the DMs that were found. And there's a few little other tweaks you can do, but basically you're just trying to pick as big a DM range as possible. And this will help us assess the quality and the robustness of our results. Okay, so what we did was we took 41 subbursts from 3 different repeater sources. They're listed here, 121102 and 2 chimes, 2 sources that were made available by Chime. And across the DM range that we chose for each of those sources, we found valid measurements at each DM for 28 of the subbursts. So 28 of the subbursts, when you try to measure the slope, you're going to get a reasonable number. And those are the points that are most displayed here. The remaining points are circled. So these needed a slightly shorter DM range. And what I mean by valid measurements is basically avoiding the discontinuity that happens when your slope is infinite, when your FRB appears to be vertical or positive. I forgot to talk about that. I'll come back though. So yeah, so here I have the prediction from our model. And there's a negative sign here. So we expect every slope to be negative. And if you want to understand this physically, what's happening is you always expect the lower frequencies to arrive later in this model because it's a relativistic model. So the lower frequencies will have a longer time dilation, and that's why they should arrive later. And that's why we should always expect a negative slope. But what we see here, so notice the scale and notice the bars on each of these points. So the bars are not uncertainties. They are the range of measurements that were found. And we argue that these ranges are much, much larger than the true uncertainties. And this is just because of how large of a DM range we've chose. And even with these massive ranges, you can see that there's a very definite trend between the 3 sources. Using the range of measurements, what we also do is we'll find a fit for each DM, and we can find a range of fits similar to how we found a range of measurements. And those are shown in the shaded regions. So note how the shaded regions are close to each other, they overlap, and there seems to be agreement between the 3 sources. So the real point here is that the existence of the trend is independent of DM choice. And this is true even though the measurement of each of these slopes is very dependent on the DM choice. But we can still see that the trend still exists, any DM choice. So I want to talk about, so if you look on my axis here, I've labeled it as slope, but are these really all slope measurements? And I have an example here of what the real problem is when you don't have a high enough time resolution in your data. So here's an example of an FRB with multiple subbursts. But at the time resolution that we have, it looks like a single burst. It's basically almost impossible to tell. It can be impossible to tell if the FRB you're looking at has multiple subbursts or is just a single subburst.
3 minutes.
So if we, 3 minutes, okay. So if we were to put this through our pipeline, we're going to get a slope. We're going to call it a slope, but really it's a drift rate. So how come we don't see many in our plot? How come we don't see many deviations from the trend or outliers, many outliers? Why aren't there 2 populations, one for the drift rates and one for the slope? So in our model, it's actually okay. The drift rate can follow the same trend as the slopes. They will be longer duration just because they're consisting of multiple subbursts, but they will still follow the trend. And that happens because they have similar delay times as the individual subbursts. So the model is a narrowband model in nature, and we can use it now with our fits, the fits that we found to make very rough estimates of the physical parameters. So for example, the rest frame frequency we can find based on the range of frequencies observed for this source, which range from 110 megahertz to almost 8 gigahertz. We can deduce that the rest frame frequency is about 1 to 2 gigahertz, and we can find other parameters like the velocities. So at the highest frequency, we expect that the velocity of the source, the emitting source is, parts of the source is very high, 90%, almost 90% the speed of light. And the bandwidth of the source is also related to the velocity. So it's directly due to the velocity. Excuse me. So in our model, the way we if we put our model glasses on and look at a waterfall, what we see is these individual subbursts, and we're going to try and understand that each of these different frequencies is coming from a different velocity sample within the emitting source. So the material that is emitting this part of the signal is moving a little faster than the material emitting this part. And yeah, so that's what I wanted to talk about today. So the existence of the trend, we see it regardless of the DM chosen for each burst. But of course, the DM choice greatly affects the individual measurements and the fit that you will find. So obviously the next questions that we want to answer is, do all FRB repeaters follow a version of this relationship? If not, are there going to be different classes between these repeaters? Did we just get lucky with the first 3 sources and they seem to line up? And then importantly, we want to use this eventually to find physical parameters of the source, like the rest frame frequency of emission, which will tell us about the underlying emission mechanism. So there's lots of data becoming available with much better time resolution. So that's great. There's the CHIME catalog with tons of new data. So some very early results of a 4th source that we've added. This is from 180301A from Luo et al., who I believe is giving a talk later in this session. So just some early, very, very early results, just to show how that fits with the other sources. But there's lots of data becoming available, and we need tools. So this is a interface I've been building using DearPy GUI. It's very fast, very lightweight, and it'll hopefully help me analyze the amount of data that is coming out of CHIME and other big telescopes. So yeah, that's all. Thank you very much. Check out these packages. Thank you to the CHIME website for their help with the data early on. Ziggy Plunis and Sriharsh Tendulkar for their emails. And yeah, thank you.
Thanks, Mohammed.
Yep.
We already have one question in the Q&A. If you have other questions, participants, please feel free to put them in the Q&A now. So the first question is, how does this DM selection give results for highly periodic repeaters compared to the repeaters with lots of uncertainty in periodicity?
Sorry, could you repeat that? How does
so how does this DM selection give results for the highly periodic repeaters compared to the repeaters with lots of uncertainty in the periodicity? I guess, do you see like that the sources that have been found to have an underlying periodicity, do they like follow this relation more closely, or?
Well, the only sources we've looked at are these 3. I believe 180916 has a periodicity. I don't know if the other 2 have a periodicity.
Yeah, 121102, it's like a tentative sort of like several 100-day periodicity. So.
Oh yeah, okay. Yeah, I guess I don't really know how to answer that. I don't think we have seen much of a difference based on what we've looked at.
No, that's great. Okay. Other questions? Okay, another question in the Q&A. Aaron Perlman, do extrinsic effects, e.g. frequency structure introduced by scintillation, impact this analysis?
They do not. I don't have a good argument. I remember we talked about this in the paper, but the scintillation will essentially not show up in our relationship, and that has to do with it has to do with how we derive this. But I'm sorry, I don't. Maybe in the Slack you can Yeah.
No, that's okay. You can, okay. And then the next question in the Q&A from Sergey is the huge data set from FAST about FRB 121102 available for such studies? It is better to look at large statistics from the single source.
Yeah, so I do have a lot of 121102 data that I'd like to get to. And there's data from FAST, I believe, and there's also data from a lot of other sources as well for 121102. Yeah.
Okay, and then we have time for one more quick question from Bing Zhang. How does the relation look like if the redshift 1 plus Z factor is considered?
So because we, I'll go back to the model here. So this term here, we have d new obs over new obs. And basically we present the data this way because the redshift correction that you would have to make cancels out once you show the data this way. So we don't have to worry about it. How does it look without? If we were to do the redshift correction, so if we were to move this new obs over to the other side, you would basically have a vertical shift between these slopes. Yeah.
Okay, there are a few more questions for you in the Slack where you've been tagged, but we do have to move on to our next speaker. So you get a chance to check that out after your talk. You can see what people have to say. Okay, so we'll move on to our next speaker, who is Joscha Jahns, who will be telling us about burst storms from 121102.
Exactly, thank you. So we have observed 121102 with this beautiful telescope that you can see on the right when it was still among us. And we monitored it regularly since it was discovered. And well, for those who are new to the field, I first want to say a few words about 121102. It collected a lot of these juicy firsts. It was the first FRB that was not detected by Parkes by another telescope, and therefore lended credibility to the field itself. It was also the first repeater that was discovered with 10 additional bursts published in 2016 by Spittler et al. And it was also the first localized source, localized to a small dwarf galaxy by Chatterjee et al. It has a lot of the characteristics that we now think are characteristic for our repeaters. So strong temporal structure, as you can see here, and also the downward drift in frequency, which we call the Sad-Trombone effect. After periodicity was discovered in R3, Reshma et al. Also reported a periodicity in this repeater, and Cruces et al. Refined it to 161 days with about a duty cycle of 60% at L-band. So since we know that source for so long, we started monitoring it right after it was discovered to repeat. So we have more than 4 years of observations now, and we usually observe once to twice a week for 1.5 hours on source and at 2 frequency bands, at 1.4 gigahertz and at 4.5 gigahertz, usually back to back, so that we have both bands on the same day. We coherently dedisperse our data and to allow for a very high time resolution of 10 microseconds. I will talk about 3 outcomes of our monitoring campaign. First, I will talk about long-term DM evolution that Andrew Seymour did a very careful analysis on. Then I will be talking about the 2018 November rain, a very active period. And then I will talk in the end shortly about burst energies in the 2016 September storm that Dante Hewitt worked and shortly, not because he doesn't have so many results, but because he's also presenting a poster at this conference. So I urge you all to go there and talk to himself about the results as well. Let's start with a long-term DM evolution. So Andrew used a structure maximizing code DM phase that is widely used now, and he only used the very well structured and usually very bright bursts in our sample. And those are plotted here in the DM versus time plot. And what you see is that the M seems to be rather stable in the beginning, but then suddenly increases in the beginning of 2018. Well, suddenly as in astronomical timescales. And then it seems to slow down afterwards again. And this is especially interesting in the light of recent results by Hilmarsson et al., who looked at the RM revolution in the same time window and found that it is generally increasing, but then there seems to be a stop in the decreasing, I'm sorry. So that it seems to stop decreasing at some point, and that is around the same window. So that will be interesting. For the rest of the talk, I will focus on two small windows here. So first and mostly I will talk about this window of the November rain. And since this window is very small compared to the DM evolution that we see, we de-dispersed all our bursts at the same DM. Yeah, for that we took the 6 best structured bursts and took the average of those. We also ignore scattering because Hessels et al. Have shown that the scattering timescale for the source is very low at L-band, and what appears to look like scattering sometimes in the burst we think is more just intrinsic asymmetric bursts. So what we did to find those bursts first, so at the right you can already see some examples of the most energetic bursts that we found. And to find those, we improved our search pipeline. We fixed what we call GPU node dropouts. This is where 1/8 of the band goes to 0 suddenly and ramps back up shortly after, and that caused a lot of candidates. Then we also improved the RFI excision. We used the full resolution data and flagged more channels than previously to flag out more narrowband RFI, and this reduced the number of candidates that we had to look at by eye, because we looked at all the candidates by eye down to so much that we could reduce our signal to noise threshold down to 5. Yeah, with all these improvements, we found 815 bursts in this November sample and 10 observations of totaling about 9 hours. The first interesting thing that we see in the data is when we only look at the burst rate. So here you can see plotted our 10 observations, and they all fall in the same active window, which is marked by these yellow lines as it was reported by Cruises et al. And you can see that one of the observations has 0 bursts in 1.4 hours, while another one has 187 bursts in only 0.8 hours, and that gives a rate of more than 200 bursts per hour. As a little side note, I also plotted as a dashed line the only detection of chime from the source, so that one was also in this very active period. So to analyze the burst, we fitted 2-dimensional Gaussians, and you will see in a second that this is very similar to what we just heard by Mohammed in the talk before. So we used 2D Gaussians, and we used least square fitting as it is implemented in SkyP, and when we had more than one component in the burst, so like this complex bursts, we fitted multiple Gaussians to it, where we decided the number by eye. And you can see that the residual for this one looks very, very good. Yeah. And we fitted more than 1,000 components like this. And yeah, we also did fit 1D fits for the weaker bursts, where the 2D fits didn't give very good results. One more thing about the exact form that we fitted, because this is important in a second. So we fitted a 2D Gaussian that looks like this here. The frequency is just described by a normal Gaussian, but in the time we added a shift to each channel. And this is very similar to what we just learned to be the slope. And I called it tilt instead, also to distinguish it from the drift that we see, although, as Mohammed said, they are very closely related. So there's 2 things to keep in mind here. The tilt is very closely related to the DM. So for this burst, for example, you could think that it is not de-dispersed enough, but we know from more structured bursts that we are we do have the right dm approximately. And then another thing is that the tilt and sigma t here are not related, because sigma t is not what we usually report. It is not the width in the time series, but it is the width at the center of the burst, and therefore it does not change when you change the angle of this or the tilt. Nevertheless, if we look at the full parameter space of our fitted model and the energy as well here, we see a very strong correlation between these, and yeah, this is in the sense that very sharp bursts have always a very small angle, and the broader the bursts, the stronger this tilt seems to be. And I will focus a bit more on this one, therefore I plotted it again with error bars here, although I left out the error bars in the x-axis, because otherwise it gets very crowded. So there's one important outcome of this, because there's three contributions basically to the scatter here and here. One is, of course, the fitting has errors, and therefore you get some scatter from just the error bars. dm variations can cause scatter because dm is very closely related to the tilt, and then intrinsic variations in this tilt. Now, the interesting thing is that we can basically exclude dm variations, because even though we de-dispersed all our bursts at the same dm, we see only very weak scatter in the sharp bursts. So the scatter must come from intrinsic variations mostly, or from the fitting. The next thing that I want to talk about is waiting times that we also analyzed. Here's a bit of a complicated plot, so I will go through it bit by bit. The waiting times, or the times between consecutive bursts, are plotted in the x-axis, and the arrival times of the bursts themselves are plotted on the y-axis. And that means we have to put all the observations in one plot. I marked green lines here for the beginning of each observation, and put those observations back to back. Yeah, there's orange points here and green points. So orange points are from subbursts of the same complex burst. So those are individual subcomponents of the same burst, and green points are isolated bursts. And you can see two peaks in the histogram up top. The first, yeah, the second, let me start with the second one. The second one is what we expect from randomly arriving bursts. So this one is Poisson distributed, and it also changes with the rate, because, well, the less bursts you have in an observation, the longer the mean waiting time between them will be. So you can see that for observations with lower rate, you have more points at the right. And on the other hand, the left peak does not seem to change with the rate, and therefore we think that this is some characteristics time scale. And yeah, it's surprising a bit that even bursts that look very distinct and are clearly separated seem to be, yeah, our interpretation is that they must be from the same event, for example, in the magnetosphere of a magnetar.
3 minutes.
Okay, thank you. And let me come to the last thing. We also looked at how this would affect the energies. So here is the cumulative number higher than some energy plotted. And the burst energies, if you just take the energy of each burst, is in green, and if you sum up the energy of one event that arrived within 0.1 seconds, then you get the orange points, and we get slightly different power law indices for those. Furthermore, we also see the overabundance of high energy bursts that was reported earlier. Now I come to the last slide, and I would present the result of Dante Hewitt. So he looked at the 2016 September storm. He did a reanalysis of those data and found 478 bursts. And up top here, you can see the exact same plot that I just showed you. So just with the rate on the y-axis, but that's and the energy on the x-axis. So you have the same higher abundance of high energy bursts. And by the way, we do think that for our case, there's drop off at the left edges from our completeness threshold. So he looked at the space of width, bandwidth, and energy, and he used a clustering algorithm with Gaussian mixture models to cluster those bursts. And the two groups that he found are marked with triangles for one group and circles for the other group. And you can see that, there seems to be two kind of bursts in there. And this might also explain for these observations the high abundance of high energy bursts here. So with this, I want to conclude and leave you with a summary slide where you can read the quick points one by one. Thanks for listening.
Thank you very much. Okay, we have a few questions coming in the Q&A. So the first one is, what software are you using in your search pipeline?
In the search pipeline, we use the pipeline that was put together by Daniele McGill, and we further improved it. It's based on the single pulse search in Presto.
Okay.
And
great. Okay, the next question, wouldn't it be better to fit for DM scattering as well, along with all other profile and spectral parameters? And how confident are you in the errors reported by the least square fitting? It tends to underestimate fitting errors in low signal to noise bursts.
That was a lot, right? So the errors in the least squares, I think generally that it seems to overestimate them, because often it is also for quite clear bursts that the error is so large that the amplitude could be zero within the 1 sigma region. What was the beginning again?
Yeah,
sorry.
wouldn't it be better to fit for DM scattering, I guess DM and scattering and all the other profile and spectral parameters?
Well, I think for the DM at least that it is that it does not make a lot of sense. Well, that's exactly what I showed you basically in this plot. That the DM scatter must be very low. So yeah, that's exactly what comes out of this. That the scatter in DM must be low, and therefore we are better off with taking one DM and sticking to that one, so that we can see the intrinsic changes in the burst profiles. Yeah, and the scattering we think is just not relevant for this source, because most importantly, if you compare it to other bursts, then you often see this what looks like scattering in the last component of the burst. And yeah, to have such a high change in the scattering in such a short time, we think is very difficult for theoretical models. Yeah.
Okay. Two more quick questions. Is there any correlation between the fluence of an FRB and the waiting time until the next burst?
Yeah, we did look at that as well, and I think a lot of other papers before have also looked at that one, and we also don't find any correlation between waiting time and energy, either after or before the burst.
Okay, and then the last question, can you re-explain the plot in slide 17? What is the difference between the energy of the orange and the green points?
Yeah, okay, so let me go one back then. So we classified as belonging to one event everything that was within 100 100 milliseconds or 0.1 second. So everything to the left here, the lower peak, we classified as one event and summed those energies up and then looked how that changes the energy distribution. Yeah, compared to just taking every single burst energy. Yeah.
Right. Okay, great. Thank you. Okay, so if you have further questions, participants, please feel free to put them in the Slack channel. And now we will move on to our next speaker, who is Ketan Sand, who will be telling us about multiband studies of FRB 2018-09-16B.
Yeah. Can you hear me?
Yes.
Can you see my screen?
Yes.
Okay. I apologize if there's any lag, so please tell me. Hi, everyone. My name is Ketan, and I'm a PhD student at McGill University and Professor Vicky Caspi. I'm showing here today the results of multi-band observation of FRB 2018-09-16B or R3 using UGMRT, GBT, and CHIME. This work is presented in cohesion with Jacob Faber's poster, so do pay him a visit to see interesting results on polarimetry, morphology, and scintillation. So FRB 2018-09-16B or R3 was first discovered by CHIME in 2018. Then the data found a periodicity of around 16.35 days in the source, which has been refined recently by Pinus et al. To 16.33 days. This is the periodicity which we'll be using in all of our phase calculations. The source is localized to our Spira galaxy around 150 megaparsecs away and has a pretty consistent DM of around 348.8. It's the first source, first until now, the only source to be detected at the low fire band of 110 megahertz, and recently it has been detected at 6 gigahertz as well. So why undertake a multiband study? Well, it's very well established now that repeaters are more or less narrowband sources. So to take a multiband study, it helps us cover a wide bandwidth and estimate any frequency dependence in the activity of the source. Also look into the variation of various properties with frequencies. That involves properties like scattering, width of the burst, drift rate, etc. And then we also can look into the frequency biases that might come due to frequency biases and periodicity that might come at us being very well shown for R3 by Pastum as well and their recent publication. And also a non-detection at a certain frequency range thus provides useful constraints on emission mechanism in predictor scenarios. In the figure on the right, I show our brightest GBT detections and simultaneously the time series in the GMRT band, and we find it clearly shows that the burst is quite narrowband and there is no signal detected in GMRT. So our observations were done using 3 telescopes, GMRT, GBT, and CHIME. We covered around 700 megahertz of bandwidth and 0.1 in phase. And one of the epoch of GBT and GMRT was simultaneous, which provided us with lots of interesting results, which have been presented in the following slides. The lines in these plots shows the arrival times of burst in our observations. So the search of the data was done using a Spandak. It's a transit-based pipeline, which is developed by Dr. Vishal. Here I present a very simplistic picture of the pipeline. It takes input filter bank file, then it does RFI filtering using the Presto's RFI find algorithm. Then it uses the DQ-based search algorithm called Heimdall to look for single pulse candidates. These candidates are then sorted using a Python-based classifier on various reasons of maximum candidates per second, the clustering of candidates, etc. And then there's also machine learning employed to prioritize the candidates in such a way that the most astrophysical of them is plotted first. So this helps in the visual analysis of the candidates, which later on we use to confirm the status of it being astrophysical or not. So we detected 4 bursts in GMRT data and 1 burst and there's a 1 burst in CHIME around the same time period, which has already been published in Pinus et al. 2021. The burst in CHIME, so the burst in GMRT shows quite a bit of interesting structures. As you can see, we see a downward drifting structure at 300 to 500 megahertz range, and it's like the first wide bandwidth instantaneous detection at such frequencies. And we also see somewhat a scattering tail in GMRTB, but this can also be some unresolved structures. Interestingly, in less than 2 hours of observation for GBT, we detected around 7 bursts. And since we had baseband data for them, we performed polarization studies on the brightest of the burst in our data set. We find a flat polarization angle and 100% and the burst to be 100% linearly polarized. But for more details on this analysis, I'll refer you to Jacob Faber's poster. We de-dispersed all of our burst around the structure maximizing DM of GBTE, the highest SNR burst in our dataset, and which came out to be around 348.8. So to understand the various structures which are seen in the burst, we obviously did the drift rate analysis. Again, the analysis results are, the procedures and the analysis are in Jacob Faber's poster. While plotting them, plotting the drift rate and whether the central frequencies of the burst which are detected, you clearly find that there's an increase in drift rate with frequency, which has been seen for other repeaters as well, and it's now well established, showing that there might be a common emission mechanisms involved with repeaters. Probing deeper into the burst structures, we estimated the scattering timescale of the burst that they showed that GMRTB showed a pretty nice scattering tail. So its scattering estimation came out to be 1.7 milliseconds, which is in agreement with what has been published for this source around similar frequencies. Our values are consistent with the power index of -4, extending from the 2.7 microsecond scattering published in Marcotte et al. With Arecibo observation of the source. GBTE does show some high scattering, but this can also be attributed to unresolved structures in the burst. But overall, our results agree well with what is expected from the source, what is expected from galactic contribution. So to probe deeper into the unresolved structures, we did a time series autocorrelation of the burst, and out of which GBTF showed us pretty clear signs of microstructures. So the width of the microstructure was determined to be around 30 microseconds. So here on the right, I show you the 4 microsecond time resolution plot, time resolution time series of GBTF. And if you just separate out a Gaussian envelope, you can very well see that there are a lot of residual peaks at that resolution. So these are since these were detected at less than 1 gigahertz, we assume that the environment is much cleaner than for R3, thus not leading to the scattering and smearing of these structures. And this also hints on the emission being microspheric in origin. Now going on to the well-established phase frequency relationship for the source, we do find more activity in our GBT band compared to GMRT band, since our observations were earlier in phase compared to the peak activity. In fact, we don't find any burst in UGMRT, whereas the FRB was hyperactive in the GBT band. So here, this plot beautifully shows the phase frequency relationship. This takes inspiration from Agarwal et al. Publication. So as you can see that all the blue or the high frequency detections are earlier in the phase, and the red and the low frequency detections are later in the phase. So since we had simultaneous observations and the burst rates of the data set, we tried to estimate the statistical spectral index of the source. The concept of statistical spectral index is given in Hubin et al. So it's basically trying to estimate the distribution of energy with frequency by taking a burst rate and the sensitivity of the telescope used in the multi-wavelength observation into account. So since we had a pretty high burst rate at GBT band compared to GMRT during the simultaneous observation, we got a higher value of statistical spectral index than what was earlier estimated by Chawla et al. For the source. But we do want to point out that our observations are earlier in phase as compared to what has been as compared to Chawla et al. So this might also hint that there's a change in energy distribution over phase. So looking into spectral energy, the burst energetics, our observation value agrees well with what has been seen for the source. Interesting thing to note is that the source has like 4 order of magnitude range in all of the energy of the burst. And obviously the low far bursts are the brightest because there's a high sky temperature and you only detect the brightest of the burst there. But interestingly, we don't see burst of same energy at higher frequencies. That might say something about the emission mechanism. Doing a comparison with SGR burst, as Marthi et al. Reported, the detections were within an order of magnitude of the energetics of SGR. But again, a distance to SGR is still not well constrained. So the plot here shows at the maximum possible distance of 11 kiloparsecs. But it does tell us one thing, that if SGRF was at distance of R3, we'll not be able to detect it. So this might be a possibility that due to lack of sensitivity, we might be missing out on a lot of weaker bursts from R3 that might affect periodicity and energy estimates. We find RM variation in our data set. Our RM value is less than what has been reported for the source. And this shows a very gradual decrease over the 2-year period of the source, which has earlier been also published in Primus et al. We don't see any relationship between RM and phase of the source, but we require more data set at different frequencies and at different epochs to make a clear confirmation about this relationship, which we find between RM and phase. So presently, we are taking an even larger campaign. We are going on with a 50-hour long campaign with UGMRT. So UGMRT has a very unique capability of using 2 subarrays simultaneously to have observation in 2 bands. So we are doing observation in band 3 as well as band 5. And then simultaneously, we are doing observations in the C band of using the GPT wake to listen backend. So this plot here shows the distribution of our observations. The dashed line shows 16.33 days periodicity, and the gray shaded region shows the so-called active window, which obviously is frequency dependent. And we have tried to cover as much of the active window as possible to disentangle and understand more difference in properties of bursts. So here are some initial preliminary results from the large campaign which we have undertaken. This plot shows the one which has been generated by Spandak. So it has 4 panels. The first panel shows you the time series of the burst which was detected. Then the panel shows the dispersed burst, and then it shows the bow tie plot of the DM versus time plot. Lastly, we show the original chunk of the filter bank data in the file, dispersed around time. As you can see, we detected an extremely high SNR burst from the source. So this does help maybe just cover up the energetics. This does hint on high energetics maybe at lower frequencies, but the analysis of the data is still underway, and we have lots of more bursts, and we'll try to present them together to give a comprehensive picture about the varying activity as well as the various spectral anomalies shown by the source at different frequencies. Okay, so just to conclude, we report here the first detections of the source in 800 to 1 gigahertz range. And we find more activity in the source in the GPT band compared to the UGMRT band, which strengthens the frequency dependence and also maybe hints on an energy distribution over phase using the statistical spectral index analysis. We observe microstructures below 1 gigahertz, hinting on the source to be, hinting on the emission to be magnetospheric in origin. And since these microstructures were not scattered or smeared out, we imagine that it has a cleaner environment compared to R1. We find an increase in diff rate peak frequencies, as what has been seen in other repeaters. And we also see a flat polarization angle in source, which again challenges the precessing neutron star hypothesis that has been presented to explain the periodicity of the source. We see a decrease in DM over the 2-year period, decrease in RM over the 2-year time scale. And we also suggest that we might be missing out on a lot of weaker detections at different frequencies, which might change the periodicity estimates, but it all depends upon the sensitivity of the telescope, and that might change with future projects. We don't see any variation in DM over frequencies as well as time. But overall, we conclude that the multiband studies are definitely one of the ideal approaches to study repeaters and even one of FRBs to maybe understand the difference in activity of the source as well as the different spectral anomalies which might see at varying frequencies. I'll again encourage you to visit Jacob Faber's poster to see the results on polarimetry, morphology, and scintillation analysis in much more detail. This work was done with immense contribution of all the fellow authors, as well as help from the collaboration in general. So I'm very thankful for their help and support. So yeah, quite early, but yeah, I'm happy to take questions.
Thank you, Ketan. Right on time, actually. Okay, so we have a few questions already. So from the, well, I'll give organizer's preference. So Jason asks in the chat, because I don't think we can use the Q&A. He asks, how did you guys correct for the ionosphere when measuring the RM?
Oh, okay, RM. We didn't have any robust. We didn't do any robust ionospheric corrections. We just took an estimate in the sense that the Plumas et al. Had very little variations in their values. But yeah, we haven't done any robust ionospheric corrections in RM values.
Okay.
That's a good point.
Next question. Yes, the next question is from Bing Zhang. It is now known that FRBs, especially repeaters, have narrow spectra. Is it still useful to derive a power law spectral index alpha?
So this is not like, as I said, it's not a straight spectral index. It's statistical spectral index. So what it does is makes a statistical spectrum of the source, in the sense that it estimates the energy distribution with frequencies for the source. So using this value, we try to estimate that the FRB is more energetic, or is bursting more at a higher frequency at this particular phase. Yeah, so it's not like a straightforward spectral index as seen for the pulsars.
Okay. Okay, are there any other questions? I see that there's a little bit of discussion happening on Slack, but Vishal is answering some things there. If anything comes in the Q&A, but I think we can finish up there and move on to our next speaker. So thank you, Ketan.
Thanks, Emily.
Yep. All right, so our next presentation will be a recorded presentation from Rui Luo, who can't make it because it's the middle of the night in Australia. But his presentation will be about diverse polarization angle swings from a repeating fast radio burst. And we also have one of the co-authors of the paper who will be here during this session to interact during the Q&A. So if you do have questions at the end of the talk, please still do put them in the Q&A, and we can discuss them there, or you can tag Ray on Slack. So, all right, we can start the talk.
Hi everyone, my name is Rui Luo. I'm a postdoc at CSIRO-ATNF in Australia. It's my great pleasure to attend FRB 2021 meeting. I'd like to thank the organizer for giving me the opportunity to present our work published in Nature last year. It's mainly about diverse polarization angle swing from a repeating FRB source. We detected forms for using the fast telescope. In this talk, I will be presenting some main results on behalf of fast collaborations, including many colleagues in NLC, Peking University, etc., etc. In the beginning, I will review the FRB background very briefly and tell you why we perform observation using the fast telescope. And later, I will tell you how we wrote the proposal and carry out the observations. And the search pipeline will be presented and later, and the detection I will tell you all the detection we made. And after that, most importantly, the polarization measurements will be presented. I will tell you the new discovery we have from the new repeater. In the end, I will summarize all of contents in this talk. And as we know, fast radio burst defines as short duration radio transients with prominent flux density. If you go beyond the definition itself, you may find more remarkable features such as dispersion, scattering, scintillation, and polarization. Dispersion can be described as a quadratic curve in the dynamic spectrum. You can see the FRB signal sweeping across the whole bandwidth. The signal at higher frequency arrive earlier than lower one. That's dispersion. And if you remove it, you may obtain the pulse profile with a scattering tail that may caused by the interstellar median. And in addition, FRB emission also be polarized, and some of them can help us to measure the Faraday rotation. At the current stage, and we can classify the FRB sample as two categories according to observational repetition. The one is apparent non-repeater. It happens randomly in the sky isotropically, and even though you do a long follow-up for these targets, you fail to detect any additional bursts from same source. And the repeater is quite straightforward. You may expect to detect multiple bursts from same source targets with identical dispersion measures. And at present, one of our biggest open question is, do all FRB repeat? Is there any intrinsic difference between the two populations? Here's the survey results conducted by FRB 2020 meeting. You can see that half of people vote yes for this question. And this debate is still very intensive, even though we have more than 600 FRB sources, and only 24 of them are repeaters. To know better the facts of the repeater compared with non-repeater, we can plot such dispersion brightness diagram. And the x-axis is actual galactic DM, y-axis can be flux or fluence. As you can see here, and most repeating events are located in bottom left, as well as the first chime large sample. And that implies most repeating events are rather fainter and low dispersed. And it means if you want to detect more repeating events, you'd better to use the large telescope due to sensitivity. And that's why we wanted to apply for observing time from the largest telescope in the world, that is FAST telescope in China. And FAST telescope has a spherical aperture of 500 meters from its name, but the parabolic aperture is actually 300 meters because of so-called active reflector technology. And owing that such design, the focus of the parabolics can be changed in real time, which enable us to track the targets in the sky for a few hours. The FAST telescope may focus on the source in the northern sky, only a small part of southern. And the operating frequency can be very low, and higher frequency can reach 3 gigahertz. And the sensitivity is high enough. It may enable us to detect very faint signal. Most importantly, this telescope has been equipped with a 19 beam receiver, which was built by CSIRO-ATNF. And this receiver has a frequency range from 1 to 1.5 gigahertz. The beam size of L-band is 2.9 arc-minute. And we submitted our FAST proposal for shared risk observational semester in 2019. And this TAC report was rated as grade B. It's not so optimistic. And most of referee thought it's highly risk proposal. How can you ensure the targets you observed is true repeater or not? And in addition, this repeater also exhibits the non-Poissonian process. How can you ensure detection? And we will only allocate 2 hours for tracking. Under such limited observing time, we have to select our targets very carefully. And the main consideration is beam coverage. For example, if you have a detection from Parkes telescope, which whose the beam size is 14.4 arc-minute, and you have to use 19 beam receiver FAST telescope to cover all the whole area. Even though it can be covered completely, you still only have 28% chance to point towards the target correctly because of gap area among different beams. Thanks to additional remetiform Parkes observer, we made final decision to use the 2 hour allocated to observe FRB 180301. This Parkes FRB was discovered by Daniel Price in the breakthrough listen observations. Its DM is 522, but the arm is rather higher than the normal FRBs. And most remarkably, this FRB exhibits band-limited feature in the waterfall plot, which turned out to be a quite unique feature among some repeaters. And our searching pipeline is based on the search software called Bear, which was developed by KJ and Yunpeng. It's very similar with most pulsar single pulse search pipeline. First, you have to do RFI mitigation to clean RFI as much as possible. And later you can do the dispersion trial with many different DM values. And after the dispersion, you can have candidates. You have to match fields them until you got high significance candidates. Our first observation was performed on 16 July 2019 with 2 hours. And in total, for the first observing, we detected 4 bursts, as all 4 bursts are located at beam 7, which is consistent with the Parkes beam size. And that means the 28% chance really happens. It makes us very, very excited. And knowing it's a new repeater, we propose follow-ups. We carry out 4 observations in total, yielding 15 bursts. Some of them exhibits down-drifting feature. That's quite common in many repeaters. To obtain such down-frequent drifting waterfall plots, we have to disperse by maximizing the structure. And in the amounts of 15 bursts, 7 of them are quite bright, which enable us to study the polarization. To calculate the rotation measure, we adopt 2 methods. The first is to fit for Stokes parameters. As we know, the Stokes parameter Q and U following the cosine function. And if you do build the Bayesian inference model, you can just input the data to obtain the posterior of rotation measure. And that can help us to constrain the measurements with good error bar. To double check if the fitting is correct, we still use the very traditional method called ion synthesis. It requires you have to maximize the Faraday dispersion function by trying different ion value. Once you got a peak here, that's ion value, and as well as the corresponding error bar. And the 2 ion values made with forms different methods are quite consistent with each other for each burst. As ion value can be ranging from 520 to 560 units. And the polarization degree, the linear polarization degree is rather high, but not 100%, which different from FRB 121102. The dispersion measure are quite consistent with each other by 2 different approach, but the DM obtained by maximizing the structure can be quite stable. With the ion values, we can plot the ion light curve to study the ion variation. We found the ion of FRB 180301 changed almost 10% within a couple of hours. And to double check if that result is correct, we use DM from burst 5 which is the brightest burst we detected. We can still find such trend. And such intensive change may imply a very variable magnetized environment of FRB progenitor. In addition, we discovered very diverse polarization angle swing from the burst profile. Here's the polarization profile for 7 bright burst. You can see the PA curve as flat and upwards and downwards, even S-shape. Such diverse signature have never been observed by any repeater before. That feature can help us to constrain the emission model to some extent. And there are two basic emission models that can account for coherent emission. The one is the synchrotron maser. It requires a compact object as a central engine. The FRB can be produced by the relativistic shock, and the other model is based on the magnetosphere of the neutron star, and it's pulsar-like model. FRB can be produced along the magnetic field line. And the difference between the two emission models are mainly reflected as the polarization feature. For the synchrotron maser, you may expect to have a very flat PA swing, and owing to because the configuration of magnetic fields far away from central engine is quite the same. But for the magnetosphere origin from neutron star, it can be diverse, just as what we observe from FRB 0301. And in addition, there's an S-cap FRB has been observed as such S-shaped PA swing. And that's all observational facts can help us to constrain the magnetosphere origin of FRB population. To summarize, we confirmed the new repeater from snow FRB sample using fast telescope. We discovered diversity of polarization angle swing, which favors magnetosphere origin of FRB emission. And the ion variation may imply very variables magnetized environment of the FRB progenitor. Now the FRB 180301 has been localized as a star-forming galaxy at redshift 0.33. If you want to know more, please refer to Joanne's talks in Plenary 9. That's all for my talk. Thank you for listening.
I know Ray can't hear us, but just clap anyway. Okay, turn on the bell. There we go. Okay, thanks to Ray, who was not able to join us here, but was able to send in that talk. Very helpful. So if there are any questions after Ray's talk, we do have several minutes for questions. Okay, so we have Bing Zhang, who's here to answer some questions that he's able to, and we'll see how far we get. So the first question is from Pawan, which is, how common is the position angle swing? How many FRBs show PA swings? This is maybe a more general question that others could answer as well.
I probably am not the best person to answer this one, but Emily, can you address at least for the for fast ones, because they're repeaters. The ones we beside this one, we observed the other one. I think there is PA swing, but most of them are flat. So I don't know how common these PA swings are.
Yeah, I would say for repeaters, they tend to be very flat in general.
Yeah, that's true. I think there's a larger sample now of bursts that have polarization information, and yeah, for most of the repeaters, it does appear that there's quite flat PAs. But for some one-offs, we do see, or apparent one-offs, we do see PA swings. I don't really have off the top of my head a fraction, but PA swings are observed for a subset of polarized FRBs. Okay. Are there other questions in the Q&A or in the chat or the Slack? I don't see anything yet, but please feel free to add some questions. I'll give people a few more minutes in case they want to type. Yes. Okay. So Asaf is wondering if there was any circular polarization seen for this source.
No.
Nice. Easy. Okay. All right. Well, I would say that that looks like there are no more questions. So if you do have questions that you think of about Ray's talk, I know he's very active on Slack when he's awake. So feel free to ask on the Slack channel, and I'm sure he will get to them when he can. So we can move on to our next talk of the session. This is Reshma Anna Thomas from West Virginia University, who will be telling us about polarization properties of a repeating fast radio burst 1905-20.
Hello, can you all see my screen properly?
Yep.
Okay. So hello everyone, I'm Reshma Anna Thomas. I'm a graduate student at West Virginia University, and I'm also a part of the Real Fast collaboration at the VLA. So today I'm going to talk about the polarization properties of FRB 1905-20, and these are the people I work with. So before going into the details about the polarization of a particular FRB, I'd like to talk about, in general, about polarization. So on the right-hand side, you can see an electromagnetic wave that is propagating in the z direction, and the vector n represents the direction of electric field. And by convention, polarization is referred to the direction or the orientation of electric field. And as you can see, it is inclined at an angle theta from the x-axis. So polarization can either be circular or linear. And when a polarized light passes through a magnetoionic medium, the plane of polarization, that is the plane that contains the direction of propagation and the electric field, that can rotate. And this rotation is quantified by rotation measure. And when this rotates, the polarization angle that we observe changes, and this change is proportional to the square of the wavelength. So what are the observables here, or what can we calculate from the telescope output? So we can calculate the Stokes parameters, I, Q, U, and V, where I is the total intensity, and the linear polarization fraction can be calculated using the square root of Q square plus U square divided by the total intensity. The circular polarization fraction can be calculated by the Stokes V divided by I, and the observed polarization angle can also be calculated from these Stokes parameters. So polarization in FRB, so far we have about 600 or more than 600 published FRBs, and a subset of them have polarization information. And on the right, you can see a histogram of the linear polarization fraction of all the published FRBs, and it is very evident that the one with the red outline, that is the repeaters, show large polarization angle, a large high linear polarization fraction, and with a flat polarization angle, with an exception in the repeater 180301, which we just heard shows diverse polarization angle with inverse duration. And non-repeaters appear to show more heterogeneous polarization properties. So in this figure, you can see on the x-axis, we have the DM of the source, and on the on the y-axis, you have the RM of the source. And the distribution of pulsars and magnetars is given in the orange dots. And the repeaters are given by the blue stars and the non-repeaters by the red stars. And it is very clearly evident that FRB 121102 is an offset from this source. So of all the published FRBs, FRB 121102 has the highest reported RM of about 10 to the greater than 10 to the power 5 radian per meter square. And from that, we can conclude that it is in the vicinity of, or it is embedded in an extreme magnetoionic medium, which is massive black holes. So we have FRB 121102 here. So before going into the polarization properties of this FRB, let me introduce this FRB to you. FRB 190520 was first discovered by the FAST telescope in China. On the right-hand side, you can see the dynamic spectrum and the time series plot of few of the bursts from this FRB. It is a very active repeater, and it has a DM of about 1200 parsec per centimeter cubed. And this FRB was localized using the real fast system at the VLA. And it is co-located with a persistent radio source, which makes this interesting. And on the right, you can see the VLA radio image of the PRS. Follow-up optical observations have identified a dwarf galaxy as its host at a redshift of 0.24. Another extremely interesting fact about this FRB is its very large DM host. So for more information about this FRB, please tune into Dealey's talk at the late breaking news session. You'll find more interesting information there. So is this FRB an analog to FRB 121102? So both FRBs are active repeaters. Both of them have persistent radio source associated with it, and both of the PRS luminosity is also similar. And both of them reside in dwarf galaxies, and both of them have similar redshift. Both of them have very high DM host. And as we saw earlier, 121102 is found to be embedded in a magnetoionic medium, but we don't know that about 190520 yet. So we followed up this source using the Green Bank telescope at West Virginia. We did L-band observations first. We observed for 7 hours. We detected about 15 bursts. And the single pulse search was done using a package called EOR, which uses Heimdall to search for the candidates. And the candidates were classified using fetch. And on the right-hand side, you can see the time series plot and the de-dispersed spectrum of one of the brightest bursts from this observation. And we searched for polarized signal in this very bright L-band burst, and we did not detect any significant polarization. And we did a brute force RM search using the software RMFit. And we did not detect any RM up to 10 to the power 6 radian per meter square. So we followed up the source using the C-band of the Green Bank telescope. We observed for 4 hours, and we detected about 15 bursts. And we searched in smaller bandwidths up to 750 megahertz. So on the right-hand side, the topmost figure shows the whole observing bandwidth, 4 gigahertz to 8 gigahertz of the C-band of GBT. As you can see, the burst that is in there is very weak because of all the added noises. Since we know that the repeater bursts are very narrow banded, it is always a good idea to search in smaller bandwidth. So as you can see on the bottom two figures, these are smaller bandwidths of the observing bandwidth, and the bursts are much stronger there. And these bursts are narrow banded and they peak at different frequencies. So if we search at the whole bandwidth of 4 gigahertz, then we tend to miss bursts. So sub-banded searches are important if the observing bandwidth is really large. Again, we did the search using your package, and then we classified using the classifier fetch. And we searched for polarized signal in 2 of the bright bursts from the C-band. We did a noise diode polarization calibration, and we did not detect any polarized signal in 2 of the bright bursts. And we searched for an RM, again using RMFit, and we did not detect anything significant up to 10 to the power 6 radian per meter square. And in the second observing epoch, that was 6 months later, we again observed using the C-band of the GBT. We observed for 10 hours over 4 days, and we detected 7 bursts. And again, we calibrated using a noise diode signal that was injected. Again, we did not detect anything significant in the RM search. And to verify the calibration, we observed a test pulsar, which was B1933 plus 16. And on the left-hand side, you can see the pulsar profile. From our observation, the white lines shows the total intensity, the red ones shows the linear polarization, and the blue curve shows the circular polarization. And on the top, you can see an upward trend in the polarization angle as well. And on the right, you can see the published profile of this pulsar at our observing frequency. And this is from the EPN archive. Since the two profile looks consistent, and we were also able to recover the polarization properties from this pulsar, we were able to verify the calibration. So these are two unpolarized bursts from our second epoch of observation. One is an 18 sigma burst and one is a 7.9 sigma burst. So we have a bunch of unpolarized bursts. And what does a non-detection of polarization mean? So it could either be an unpolarized FRB, or it could be depolarized due to a very high RM. So how does that happen? That can happen due to the channelization of the bandwidth. And the intra-channel rotation is given by this, which is proportional to the channel bandwidth and inversely proportional to the cube of the center frequency. And the fractional depolarization is given by this. So if we assume, like most of the other repeaters, this repeater is also 100% linearly polarized, and if we assume a 50% depolarization, then for our channel bandwidth of 0.366 megahertz and a center frequency of 6 gigahertz, we get a lower limit for our RM to be 10 to the power 6 radian per meter square. This is pretty large. And if the RM of the source is greater than this, then we won't be able to detect anything in our observing setup. So what does this mean? From the fast data, we have a DM host. And if we assume that the DM host and the RM is from the same environment, then we can calculate the average line of sight magnetic field, which comes out to be, pretty large. So if we believe this RM to be real, or non-detection to be real, and then the DM-RM picture, which I showed earlier, will change like this. And as you can see, this FRB is even higher up here, even higher than the 121102 FRB. So that makes it interesting. So that brings me to the summary of this talk. So we have this FRB 190520, which is an active repeating FRB. It is analogous to 121102 in many different ways. But we have not detected any RM so far, and we have not detected any polarization signal detection. So all these analysis is very preliminary, and we still have a lot of confirmations to do and work to do. So also for more information about this FRB, please see Deely's talk at the late breaking news session. Thank you.
Thank you. That's really interesting stuff. All right, so we have a couple of questions so far. So X is asking, what is the path posterior probability for assigning the dwarf galaxy as the host, allowing for an unseen prior greater than 0, like 50%?
I don't know about it. I'm pretty sure D will be able to answer it because he did most of the work on the FRB. I'm just introducing the FRB.
Okay, yeah, I think there's some discussion happening on Slack as well, I now see. Okay, the next question from Vishal, what are the typical burst widths at C-band?
C-band, about few less than 10 milliseconds on an average. Yeah.
Awesome. Okay. And then let's see, we have one question on the Slack channel. Are there any plans to observe the source at higher frequency, i.e. higher than C-band? Would that help in estimating the RM?
We haven't thought about that yet, but so the signal to noise or the burst energies are seen to decrease. The signal to noise of the bursts are seen to decrease from L band to C band. So we are a little doubtful that if we observe above C band, then we may not be able to detect higher signal to noise burst. And if we don't have enough signal to noise, then it'll be even harder to detect a polarized signal if it is not 100% linearly polarized.
Yeah, that makes sense. Okay. Oh, and then we have a question from Daniele. Do you have baseband data? An extreme RM could cause a splitting in the profile. Did you calculate what is the minimum RM that would produce a splitting in the profile that you could observe at L band?
We don't have baseband data. And yes, we have not calculated the splitting.
Okay. All right. Are there any further questions? I don't see anything coming up immediately, so we will end there. Thank you, Reshma. That's really interesting stuff. Okay, and then we will move on to our final talk of this session. This will be given by Henning Hilmarsson from the MPIfR. Henning, are you online? Yes, okay. So Henning will be talking to us about polarization and scintillation properties of FRB 2020-11-24A.
Yeah, can you see my slide?
Yes.
Excellent, excellent. All right, so thank you everyone for tuning in. So today I'll be talking about the polarization and scintillation properties of the repeating FRB source, FRB 2020-11-24A. So first, let's look at how this FRB became really popular overnight. So at the end of March this year, an ATEL from Chime came around stating that this FRB was very active. And over the next few weeks, a lot of effort was put into observing it with telescopes all over the world. And this effort paid off, as within a few weeks, it was localized with multiple telescopes. Its host galaxy and redshift were identified, and a coincident persistent radio source was discovered, which seems to be associated with star formation in the host galaxy. So the work presented here is based on two papers, one on the polarization properties of the FRB using data from Effelsberg, and one on the scintillation properties using the Effelsberg data, along with detections from GMRT. So we observed FRB 2020-11-24A with Effelsberg on April 9th using the 7-beam receiver at 1.4 gigahertz. The full bandwidth is around 300 megahertz, but the bandpass drops off sharply around the band edges. So we have roughly 250 megahertz of usable bandwidth. And we recorded baseband data, so we were able to obtain coherently dedispersed archives with full Stokes information. And our observations lasted 4 hours, and we detected 20 bursts. And here we can see the massive family portrait of our bursts, where for each panel we can see the PA on top, total intensity in black, linear polarization in red, and circular polarization in blue in the center, and then the dynamic spectrum at the bottom. And the horizontal light blue lines are sapped channels. And our detections translate to a very high burst rate of 5 bursts per hour in our observing window. And we found the burst arrival times to follow a Poissonian distribution. And in many of the bursts here, we see obvious resolved scintillation patterns in frequency, which we will take a better look at later on. So here on the right, we have a closer look at our multi-component bursts. The numbers in the top left of each panel show the time and frequency resolution of the panel. And using the structure optimizing DM search code DM phase on our multi-component bursts, we obtain an average DM of 411.6 parsecs per cubic centimeter that we apply to all of our bursts. And as expected for repeating FRBs, we see a downward drift in frequency over time in many of the bursts, and all our bursts have a high fraction of linear polarization, and a few of them have a small but significant circular polarization fraction, up to about 20%. And like for most repeating FRBs, we see flat PAs across each burst. And we also note that the full width half-max burst width of our sample is quite high, with a mean width of 9.5 milliseconds, and the narrowest burst being 4.7 milliseconds. So here we can see some strong bursts from our sample that have circular polarization. And this is the first clear evidence of circular polarization from a repeating FRB. So we can compare the profiles of our sample to the Magnetar AXP J1810-197. And we see some striking similarities. So a high linear polarization fraction with small but significant circular polarization fractions. And additionally, the PAs of the Magnetar are flat to slightly slanted, similar to our sample. So we consider if the circular polarization is due to Faraday conversion, where linear polarization is converted to circular in magnetoactive plasma. So the scale of our RM changes of 10 radians per meter squared, which we will get to in a minute, and a host DM on the order of 100 parsecs per cubic centimeter corresponds to a magnetic field with a cyclotron frequency 9 orders of magnitude lower than our observing frequency. But Faraday conversion should occur when the cyclotron frequency approaches the observing frequency. And also with our low circular polarization fractions, the Faraday conversion is incomplete. So the fraction should be higher in the lower part of our band. And we don't see any evidence of circular polarization being contained within specific subbands. So Faraday conversion is unlikely, and we assume that the circular polarization is intrinsic to the source. And here we can see the rotation measure over time for our bursts. So to obtain the RMs, we used RM synthesis using RM tools. And on the left, we have the RM over time with the solid line indicating the mean RM value. And on the right, we have the Faraday dispersion function with the dotted line indicating the mean RM. And the top of each curve on the right corresponds to the arrival time of our bursts, and all the peaks are scaled to be the same height. So our RMs have an apparent variation with a mean value of -605 radians per meter squared, and their standard deviation is 11 radians per meter squared. And we also see that the bursts with circular polarization have the most extreme RM values, which are plotted in red in the left plot. So the question is whether this variation is real or that the RM is stable and the errors are being underestimated. So the errors are estimated from the width of the peaks here on the right, scaled by their height. However, if we simply fit a Gaussian to the curves and look at the 1 sigma spread on the right in red, we see that the mean RM is contained within all of them. So we hope that future RM measurements of FRB 2020-1124A will help answer this question. And if we look at the PA over time for our sample in the top panel here, we see that it is fairly stable with some burst-to-burst variation. And note that the time axis here is not in relative arrival time, it's just simply one burst after the other for clarity. And in the bottom panel, we derotate our bursts to the mean RM value instead of their individual RM values. And we see the PAs showing a bit larger burst-to-burst variation. So we can compare our findings to two other well-investigated repeating FRBs, FRB 121102 and FRB 180916B. So all three exhibit high fractions of linear polarization, a downward drift in many of their bursts, and flat PAs across bursts. And one of the many suggested origins of FRBs involves magnetars within supernova remnants, where we can use the RM as an indicator for how old the source is. And in this case, we find FRB 2020-1124A to be around a century old. And this age fits with the non-detection of an associated compact persistent radio source, similar to the case of FRB 1809-16B, while the presumably young FRB 121102 has an associated compact persistent radio source. And within our 4-hour observing window, we didn't find any evidence of periodicity, but that's not a surprising result given the periodicity of 16 and 160 days of the other two repeaters. And if FRB 2020-1124A is periodic in its activity, we will probably see something similar to FRB 121102, where bursts will seem clustered in time until a periodicity is found. So here we can see the scintillation spectra for our bursts. The big plot on the right shows the Effelsberg bursts over time, and the smaller one on the left shows the spectra for the GMRT bursts near the strongest detection of that observation, which is shown in blue. And we can see that nearby bursts show similar scintillation patterns, and through correlation of spectra between pairs, we can obtain a scintillation timescale. And this is the first measurement of a scintillation timescale for an FRB, which was enabled by our high burst rate. So yeah, correlating all burst pairs in their overlapping channels allows us to obtain a scintillation timescale. And for Effelsberg, all pairs of bursts were correlated. And for the GMRT, we considered only correlation of bursts with the brightest burst and obtained a timescale of 13 minutes for Effelsberg and 8 minutes for GMRT. And through autocorrelation of the spectra of the brightest GMRT burst and 4 Effelsberg bursts that span the entire band, we obtain a power law index for the scintillation bandwidth of 3.5, which is a bit shallower than for a Gaussian scattering disk or a Kolmogorov spectrum. Now, if we look at the scattering of FRB 2020-1124A, we see that it is heavily underscattered. So the plot in the upper right shows the tau dm relation for the Milky Way dm contribution. And there we can see FRB 2020-1124A as the green point. And then we also see some other FRBs and nearby pulsars with scattering measures. So FRB 2020-1124A is underscattered by a factor of roughly 20 with respect to NE 2001. So to investigate why, we looked at an H alpha map around the FRB shown in the bottom figure. And the plot is centered on FRB 2020-1124A, but we see the locations of nearby pulsars and FRB 121102 as well. And although H alpha emission is a tracer of ionized hydrogen and it's proportional to scattering measure, it's not directly correlated. So we can see that some of the nearby pulsars also lie in low H alpha regions, yet they fit nicely in the tau dm distribution in the plot above. A more likely explanation is that FRB 2020-1124A is towards the galactic anticenter, and the electron density maps might be overestimating the galactic dm contribution towards that direction. And the NE 2001 model is also smooth, while scattering is known to be a bit patchy. So FRBs could therefore be useful to help improving the electron density maps. So the scintillation velocity we obtain is upwards of 50 kilometers per second, assuming a scattering screen 2 kiloparsecs away from us. And this velocity is higher than the velocity of Earth, so the transverse velocity of the dominant scattering screen is either tens of kilometers per second, or the scattering screen is closer to Earth.
3 minutes.
And by measuring the And by measuring the annual variation of the scintillation timescale, we could obtain the geometry and distance of the scattering screen. So if we look at the scattering strength with distance for NE 2001, we see two possible scattering regions highlighted here in the middle with the red squares. So the top case is for a scattering screen in the second spiral arm, 2 kiloparsecs away. And the bottom case is for a scattering screen in a local environment 400 parsecs away. So the plots on the right show the measured scintillation velocities and the velocity of Earth as the dashed line. So the model predicts that scattering is dominated at 2 kiloparsecs, meaning the top case here. But if instead the scattering is at 400 parsecs, or the bottom case, then it could solve the low scattering problem, as the dm related to the scattering would be way lower, and the scintillation velocity over time is almost consistent with Earth's velocity, as we can see in the plots on the right. So for FRB 2020-1124A, we see some of the typical markers of most repeating FRBs. High linear polarization fractions, downward drift in frequency over time, and flat PAs across burst envelopes. And interestingly, we also see small but significant circular polarization fractions in a few of the bursts, which is a first for a repeating FRB. And we see a variation in RM over time. However, it is yet to be determined whether this variation is intrinsic to the FRB or if our RM errors are being underestimated. And we were able to measure a scintillation timescale due to our high burst rate, which is also a first for an FRB. And finally, we see that FRB 2020-1124A is underscattered by a factor of 20 with respect to NE 2001. But this could be the result of electron density maps overestimating the galactic DM contribution towards this line of sight. Or alternatively, this problem could be solved if the scattering screen is around 400 parsecs away. So yeah, that's all I have. Thanks for your attention.
Thanks, Henning. All right, we have several questions already. So Jason asked a question in the chat. 2 questions, actually. First, have you tried fitting a single RM and PA to all bursts jointly? And second, is the receiver natively linear or circular basis?
Hang on. I think it's linear, but someone might shoot me later if I'm incorrect, but I think it's linear.
You can always get a correction on the Slack channel. It's not a big deal.
Yeah, yeah.
But have you tried fitting a single RM and PA to all bursts jointly?
What do you mean by fitting PA to the bursts? We tried applying. Yeah.
I was going to say, I just meant, have you tried, for instance, forcing the PA to be the same between all bursts and then allowing RM to vary, or vice versa, or both together? You showed one plot that suggested that you took the average RM, but that's a bit of a different thing than what I'm asking, I think.
Yeah, so I had a thought about like, what if the PA is the same for all, but I felt like it would be not time wasting, like too time consuming to to find it out.
Okay, so because for the first repeater, we actually got a pretty good fit with a constant PA within an observation. So it would be something to investigate.
Oh, cool. Yeah, it's a good suggestion. Yeah, thanks.
Yeah, thanks, Jason. Okay, so there's a few in the Q&A. Let me just start at the top. Ben Stappers has asked, says, very interesting work. Have you considered the influence of the scintillation on the estimation of the RM errors?
No, I have not. So, so I'm presenting the scintillation results for Robert Main, so I might not give satisfactory answers on that topic. But yes, yeah, we haven't considered the scintillation in regard to RM.
Okay, yeah, maybe you can follow up in Slack with Robert.
Mm-hmm.
Okay, yep. Casey Law is asking, would you describe any of the 2020-1124A burst spectra would you say that they have multiple components with a downward frequency drift, or sad trombone?
Yes, absolutely. Yeah, I mean, we in the paper we have the calculations for the drift rates. Yeah, I mean, we can see here, for example, like 9 and 16 are obvious drifty candidates, and yeah, then we have some of the multi-component bursts are pretty clear here as well.
Yeah. Okay. And Jenny is asking, on slide 16, do you only consider single scattering sheets? Could a combination of both possible sheets explain the full scattering?
That's a good question. I think it's only a single scattering screen that's being estimated here.
Okay, that makes sense. And
But,
if you were to combine the two, so you have the two here, the two cases, if you combine the two, do you think you would explain the full scattering effects that you see?
I honestly have no idea. I think this would be better referred to Rob in the Slack channel.
Okay, great. And then a question from Shami. In this case, with broad burst components, how do you tell apart DM changes from downward drifting subpulses?
Sorry, can you repeat that?
Yeah, in the case with broad burst components, so where you have really broad components, like you see, yeah, on this slide, for example, how do you tell apart changes in the DM from downward drifting subpulses?
Well, we just apply a singular DM for all the bursts based on the average of these guys, but do you mean like calculating the DM for each subcomponent instead of the whole thing, or instead of the thing as a whole, or?
I guess maybe he's asking like from burst to burst variations. I guess so here you're taking the average of the DMs that you've felt.
Yeah, I mean, we didn't see a big of a variation. It was hovering like plus minus 1 and some yeah, 1 point something at maximum between the bursts, like for the whole sample, but all these were fairly consistent. So we just decided to take the multi-components because that's where DM phase shines, let's say, for the multi-components.
Okay. All right. I don't see any other questions in the Q&A, so we can defer for future questions to the Slack channel and conclude here. We're a few minutes early, but no one's ever mad about that. So thank you to all of our speakers from this session. And if you are interested, you, the speakers, and you, the participants, are interested in following up on any of the results presented in this session, I encourage you to follow up in the Slack channel or in one of the coffee breaks on GatherTown. And just a reminder for all of our postdoc and younger, career younger people in the audience that immediately following this session, there is a PhD postdoc mingle in the GatherTown for anyone who is interested in joining. So that applies to PhD students, postdocs, or bachelor's, master's students who just want to say hi and socialize a little bit. So please join us in the GatherTown. I think that's meant to start on the hour, but you could really join anytime. Okay, I think that concludes the session, and I think we can stop the recording.